Good afternoon, everybody. So today we will just continue our lecture regarding design and analysis of experiments, MSE133. In the context of experiments, observational studies, and surveys, we make our actual measurements on individual observational units. And these are commonly people in the social sciences, but can also be schools, social groups, economic entities, archaeological sites, and others. In some complicated situations, we make measurements at multiple levels, which makes the definition of experimental units more complex. Now, we use the term population to refer to the entire set of actual or potential observational units. For experiments, the definition of population is often not clearly defined, although such definition can be very important. Often, we consider such a population to be theoretically infinite, with no practical upper limit on the number of potential subjects we could test. But for most studies, other than a census, only a subset of all of the possible experimental units of the population are actually selected for study. And this is called the sample. An important part of the understanding of the idea of a sample is to realize that each experiment is conducted on a particular sample, but might have been conducted on many other different samples. So for theoretically correct inference, the sample should be randomly selected from the population. If this is not true, we refer to this sample as a convenience sample, and we lose many of the theoretical properties required for correct inference using a convenience sample. Even though we must use samples in science, it is very important to remember that we are interested in learning about populations and not samples. So inference from samples to population is the goal of a statistical analysis. The central tendency refers to way of specifying where the middle of a probability distribution lies. And we can use these different parameters in order to describe this central tendency. So we have the mode, the mean, and the median. So basically, the mean is the average of a data set. The mode is the most common number in a data set, while the median is the middle of the set of numbers. And I actually placed here some hints to remember the difference. Like for mode, L mode is a French word that means fashionable. So it also refers to a popular way of serving ice cream. So therefore, mode is the most popular or fashionable member of a set of numbers. You may also use this hint, like the word mode is also like most. In order to remember mean, the mean requires you do arithmetic. So adding all the numbers and dividing. So that's the mean, 1. While the median has the same number of letters as middle. So median is the middle term. Another interpretation of mean is the fair distribution of outcome, in the sense that if we sample many values and think of them as one outcome per subject, the mean is result of a fair redistribution of whatever the outcome represents among all of the subjects. In addition, the median is the value that splits the distribution in half, so that there is a 50-50 chance of random value from the distribution occurring above or below the median. Next is the spread of distribution. So the spread of a distribution most commonly refers to the variance or standard deviation parameter. although other quantities such as interquartile range are also a measure of spread. When you say population variance, this is the mean squared distance of any value from the mean of the distribution. But you only need to think of it as a measure of spread on a different scale from standard deviation. On the other hand, the standard deviation is defined as the square root of the variance. It is not as useful in statistical formulas and derivations as the variance, but it has several other useful properties. So both variance and standard deviation are commonly calculated in practice. Remember that the standard deviation is in the same unit as the original measurements from which it is derived. When the standard deviation of repeated measurement is proportional to the mean, then instead of using standard deviation, it often makes more sense to measure variability in terms of the coefficient of variation, which is basically the standard deviation divided by the mean. Another concept that we need to remember is this skewness and kurtosis of a distribution. When you say population skewness of a distribution, it is a measure of asymmetry. And the population kurtosis is a measure of peakness or flatness compared to a Gaussian distribution. So if a distribution is pulled out towards high values, meaning to the right, then it has a positive skewness. If it's pulled toward lower values, then it has negative skewness. If you have a symmetric distribution, say a Gaussian distribution, that means the skewness is 0. The population kurtosis of a distribution measures how far away a distribution is from a Gaussian distribution in terms of peakness versus flatness, as I mentioned a while ago. So compared to a Gaussian distribution, a distribution with negative kurtosis has rounder shoulders and thin tails, while a distribution with a positive kurtosis has a more sharply shaped peaks and flat tails, as you can see from this figure. Another thing that you need to remember is that parameters such as population or population mean and population variance are fixed quantities that characterize a given probability distribution. So the skewness characterizes symmetry and kurtosis characterizes symmetric deviations from normality. Corresponding sample statistics can be taught as a sample estimates of the population quantities. Next is the difference between covariance and correlation. So for two quantitative variables, the basic parameters describing the strength of the relationship of these two variables are covariance and correlation. And for both, larger absolute values indicate a stronger relationship and positive numbers indicate a direct relationship, while negative numbers indicate an indirect relationship. For both, a value of 0 is called uncorrelated. Covariance depends on the scale of measurement, while correlation does not. And for this reason, correlation is easier to understand. Although if you will see that covariance is used as an intermediate in the calculation of correlation, as you will see from our example later. Remember also that correlation describes both the strength and direction of the linear relationship between two variables. So correlation may have a value ranging from -1 to +1. If you have a negative correlation, it indicates an inverse relationship. such that population units that are low for one variable tend to be high for the other variable, while positive correlation indicates a direct relationship such that population units that are low in one variable tend to be low in the other variable. Now, if you get a zero correlation, meaning uncorrelated, it indicates that the best fit straight line for a plot, say x versus y, is horizontal, suggesting that there is no relationship between the two random variables being observed. And technically, independence of the two variables implies that they are uncorrelated, but the reverse is not necessarily true. Okay? As an example, let's take a look at this table. So this is a case of 4 variables. The row here represents the correlation. Okay? As with all correlation matrices, the matrix is symmetric with a row of 1s on the main diagonal. And for some actual population and variables, we could actually put numbers instead of symbols in the matrix, and then make statements about which variables are directly versus inversely versus not correlated, and something about the strengths of the correlations. Remember, guys, that there are several ways to measure correlation for categorical variables, and choosing among them can be a source of controversy that we will not cover in our discussion. But for quantitative random variables, covariance and correlation are mathematically straightforward. Now, if you want to calculate the covariance between x and y, that is simply equal to the integral from negative infinity to positive infinity of x minus mu x multiplied by y minus mu y f of xy dy. So mu x and mu y here are the mean of x and mean of y respectively, while f of xy is the joint PDF of x and y. Now, for discrete random variables, we can simplify this equation. We have covariance of xy is simply equal to the double summation x, an element of x, y, element of y, x minus mu x, y minus mu y, multiplied by f of xy. Remember that x and y here are the respective supports of x and y. As an example, let's consider a population consisting of all of the chickens of a particular breed belonging to a say large multi-farm poultry company. For each chicken in this population, we have x equal to the number of eggs laid in the first week of January, and y equal to the age of the chicken in years. So the joint PMF of x and y is actually given in this table. As usual, the joint PMF gives the probabilities that a random subject will fall into each combination of categories from the two variables. So from this table, we can actually calculate the marginal mean number of x from the marginal distribution of eggs. So if you want to, say, calculate mu sub x, all we need to do is to follow this formula. So mu sub x is simply equal to 0 times 0.0 35 plus 1 times 0.4 plus 2 times 0.25, and that is equal to 0.9. So where did we get these numbers? So that's basically 0 multiplied by this one, 1 multiplied by this one, and 2 multiplied by this one. Okay, so we are actually getting the marginal distribution of eggs. Okay, the marginal mean number. If you want to calculate mu sub y, all we need to do is to follow that line of solution. So basically it's 1. Okay, so that's 1 multiplied by 0.25. 1 times 0.25 plus 2 times 0.4, and then plus 3 times 0.2 and 4 times 0.15. So using your own calculator, you may verify this as 2.25. Okay, so that's basically how you calculate the marginal mean number of y. And from here we can calculate the covariance. Okay, because if you want to determine the correlation between x and y, that is denoted by this rho, this is simply equal to the covariance of xy divided by the standard deviation of x and the standard deviation of y. Okay, so the calculation steps for the covariance are actually shown here. Okay, so basically you need to tabulate your x and y and their combinations. Okay, so 0 combined with y values. Okay, and then 1 combined with y values again, and so on and so forth. Okay, and then you simply follow this. That means 0 minus 0.9, that's negative 0.9, and then 1 minus 0.9 is 0.1, 2 minus 0.9 is 1.1, and so on and so forth. And that is also followed in column 4. Okay, so if you take a look at column 4, these values were obtained by subtracting 2.25 from 1. So that's 1 minus 2.25, so you have negative 1.25. 1 minus negative 1.20 minus 2.25 is negative 1.25, and so on and so forth. Okay, now this PR here were actually taken from this table. Okay, so these are the values of your PR. Okay, so you have 0, 1, the combination of 0, 1 is 0.1, so that's why here we have 0.1. So after tabulating this third column, fourth column, and fifth column, all you need to do is to follow the formula that I gave in order to calculate the covariance. Okay, so that's PR multiplied by x minus 0.9 multiplied by y minus 2.25. So for this particular row, that is 0.1 multiplied by negative 0.9 multiplied by negative 1.25, you'll get positive 0.11250. Okay, and then you actually do that for the remaining numbers, and then you get the sum. So if you get the sum of this number, it will total to 0.075. Okay, now since our equation for correlation requires standard deviation, all we need to do is to calculate the covariance. So say for the variance rather. So if you want to calculate the variance of x, so that's delta squared sub x basically you do this solution, so that's 0 minus 0.9 squared multiplied by 0.35 plus 1 minus 0.9 squared multiplied by 0.4, and then plus 2 minus, so that's 2 minus 0.9 squared multiplied by 0.25. So remember that this 0.9 here is actually the mu sub x. Okay, so that's how you obtain your variance. So if you do your calculation here, you'll get that sigma squared x, or the variance of x, is 0.59. You get the square root of this. That would serve as your standard deviation, and if I'm not mistaken, this is 0.7681. You may verify this with your calculator. And then you do this, repeat this process for y, okay, variance of y. If you do the math, you should be able to obtain a value of, standard deviation of y is actually equal to 0.9937. Okay, and so if we go back to the equation for the correlation, we simply substitute the value of covariance, so that's 0.075, and then the standard deviation along x, which is 0.7681. You multiply this by 0.9937, you'll get a value of 0.0983. Okay, so that is the value of a correlation, or of the correlation. Now if you take a look at this value, 0.0983, it's positive. Okay, so meaning there is a correlation, but it's a weak positive correlation. And from our problem, we can actually conclude that older hens actually lay more eggs. Okay, so that's the conclusion that we can derive from the quantities that we have obtained. So I hope you understand our calculation, and with that, your activity is to repeat the sample problem for calculating the correlation and covariance, but this time you add another value for x and y. That is, if you take a look at this table, you have another row and column. Okay, so we have 5 for the number of years, and then 0.15, 0.05, and 0.15. Remember guys that this number here, okay, numbers here in the fifth column were obtained by simply adding this number. So that's 0.1 plus 0.1 plus 0.05, you'll get 0.25, 0.15 plus 0.15 plus 0.1, you'll get 0.4, and so on and so forth. Okay, so with a question mark placed here, you can obtain that by simply adding these 3 numbers.